Now I'm going to start to talk about moment about axis. So far what we talked about was calculating the moment about a point, but what if we want to find the moment about the axis? If we have one axis and find the moment about that. For example, if you consider wheels in a car, when the wheels rotate, the wheel rotate about the axis that connect the wheels together. So if you want to find the moment of rotation for those wheels about the axis connected to that, how we are going to do that. So rather than calculate the moment respect to the point, we calculate the moment respect to the axis. The other example is that when the door closes and open, you have the hinge, the axis of the hinge, and want to see the moment about that axis of the hinge. What's the moment about that axis to that? If we the easiest way is that if we have the distance, the normal distance from the force to the axis, it's just we do it like that, force times the normal distance. It's the same thing. So for example, assume I have the x, assume I have the x, y, and z, and in this format, assume I have a force that is I have vertical force, like that's the F, and then I call this distance is D in the y direction, and this the distance D in the x direction. So I want to find the moment of force about any axis. I will go, for example, for moment of force about the x-axis is the force, and it's because I have the normal distance here, I can just times it by normal. So the force times the normal distance from the force to that axis, which is going to be dy. About the direction, because this is a 3D calculation, this time we are not using the clockwise or counterclockwise, rather than use the right hand format. So we look at which direction it's going to rotate. We put our forefinger, we curve forefinger in the direction of the rotation, the forefinger of the right hand, and the thumb shows the direction of the moment. If the direction of moment is in the positive direction of the axis, is positive. If the thumb is in the negative direction of the axis, then it's going to be negative. For example, here, if you look the F rotates like that about the x, so mx is going to be rotating like this about the x-axis. So if I put my forefinger and rotate it, and then my thumb is going to be in the direction of the positive x, so its magnitude is going to be positive. What about the y? So about the y, again, we have the magnitude, and since we have the normal distance between the force and the axis, we use that normal axis, so it's a dx. What about the direction of the rotation? So if you look at the F about y-axis, it's going to rotate like this. So it's going to rotate about y-axis like that. So if I put my forefinger, right hand forefinger, and get the rotation in the direction of rotation, my thumb shows the direction of the moment. So my thumb, it says the direction of the moment is in the negative direction of the y. So if this is a positive y, my thumb is in the negative direction, so it's going to be negative. So the moment of that y, because it's the vector of moment is negative, so it's going to be negative. So remember, in this format, we have the rotation and the vector. The vector is always perpendicular to the rotation itself. So if it's rotate this way, that's the vector of the moment, and here for the rotation, that's the moment. So that's your forefinger shows the direction of the rotation, then your thumb shows the direction of the moment, and the direction of moment defined if it's positive or negative. If it's the direction of the positive axis, so it's positive, is in direction of the negative axis, it's going to be negative. So that's how we do it. If we can get the direct distance between the force and axis, but sometimes we cannot. If we cannot get that, you assume we have a more general cases that for example, we have x, y, and z axis, and then we have an axis. Assume that we call it a, and then we have the forces F, and want to find the moment of that force about that axis. So everything in 3D. In this case, the magnitude of a, remember here also these are the magnitude, not the vector. So these are the magnitude. The magnitude of the moment about that A axis, so about that AA axis, is the UA cross product R F. So sorry, dot product cross. So UA dot product R cross product F, and it's because it's the dot product here. It's going to be the magnitude. It's going to be the scalar. So what are these values? The UA is the unit vector along that axis. We want to find the moment about the axis. So that's the UA, is the unit vector around that. The R is position vector connecting the axis to the force. So it goes from, for example, here to here. So that's the R, and the F is what you have. One point about the R is that the R should start from the line of action and should end on the, should start from the axis and should end on the line of action. So it doesn't matter if it goes somewhere else. If I extend the line of action on my force, for example, like that, at any position vector that start from here, from that axis, and end at that line of action is also acceptable. So also that can be R, or that can be R. So any of them can be R. Any vector that start from the line, from the axis, and end on the line of action of the force can be considered as a R. That's one point that we need to know about that. So that's how we are calculating it in 3D if we cannot find the normal distance. So if we have the normal distance between the force and axis, this is how we calculate it. If we don't have the normal distance between force and the axis, this is how we calculate it. And remember, this is the magnitude. So eventually, after we calculate the magnitude to get the vector of moment about point 8, just like before, is the magnitude of the vector times the unit vector, unit vector along that axis. So we can get the vector format of F about axis A like that. So we said that if we want to find the moment of force about any axis, this is the equation we use that. So we have the unit vector along the axis and dot product of position vector goes from any point on the axis on any point on line of action of the force cross the force itself. So this is what we're going to get it. To calculate that, if we can write the UA as UAXI plus UAYJ plus UAZK, and we have the R is going to be RXI plus RYJ plus RZK, and we have F is FXI plus FYJ plus FZK. So if we write these three in the form of vector, that M about axis, that's M about axis A. So the M about axis A, this axis A is the axis A. So m about axis A would be find from this determinant, which is going to be the UAX, UAY, and UAZ, and then you have RX, RY, and RZ, and you have FX, FY, and FZ. So this is the magnitude that you are going to get. So it gives you the magnitude of moment about the axis A, and if you want the vector about A is again is the magnitude times the unit vector. So we can, when we want to find that equation, first we write all the these three components. We write the unit vector, position vector, and force as a vector I, j, k, and then we use the x, y, z component in this determinant to find the magnitude of the moment about that axis, and then we use this equation, which we already have the UA here, and you have this magnitude. We just need to times this magnitude to this UA, and it gives us the moment in a vector about axis A. Okay, let's look at an example. Here we have an example 1 to find the moment of F1, F2, and F3 about X, Y, and Z axis. So here we have the F1, which is parallel to the Y. We have F2, which is parallel to the X, and F3, which is parallel to the Z axis. So we have three forces, three axes, and want to find the moment about them. So we'll start with the moment about the x-axis. So for the moment, for example, start with the force 1, the F1. So the magnitude of the force is 100, and the distance, the normal distance of the force to the x. So this is the x-axis, and it's going to rotate it like that. It's going to rotate it like that. So that's the distance about that. So if I extend it, and that's the distance. So here, that's the distance going to rotate it. So the distance is going to be 3. Is it going to be positive or negative? So it's going to rotate it like that. So there is the rotation, and then my thumb is going to be in the positive direction of the x. So it's going to be positive. Now I go for this second one, the F2 respect to x. So the F2 respect to the x, the magnitude is 50 times, and the distance, because it's parallel to the x, because the F2 is parallel to the x, is not going to generate any rotation. The axis and the forces are parallel. There is not going to make any rotation. So there's no distance between them, as there's no rotation between them, so it's going to be 0. And for the third one, so for the third one also, for the F3, so look at the F3. So the magnitude is 200, the magnitude of the force. And the hand of the force that's rotated, if I extend that, and the normal distance between that and the x is 2 meters. So that's 2 meters. Its direction, so it's rotating it like that. So it wants to rotate it like that. If I put my forefinger in the rotation, so my thumb is going to be in the negative direction of x. So it's going to be negative. So it's going to be my m about point x, which is going to be negative 100 Newton meter. So that's the four moment about axis x. So the point is that if we have a force parallel to the axis, that force parallel to the axis does not create any moment about that axis. Now about moment about y-axis. So again, it starts from the F1. So look at the F1. So the magnitude is 100, and F1 is parallel to the y. Because it's parallel to the y, it's not making any rotation about the y. So it doesn't make any moment. So there's no moment about the y-axis. Then I go for the F2. So the F2, the magnitude of the force is 50, and the distance, the normal distance that's rotate about the x, so its normal distance between F2 and, sorry, about the y is 3 meters. And if I look at which direction it rotated, is rotating it like that about the y-axis, and my thumb is going to be in the positive direction of y, so is sign is also be positive. And for the F3, if you look at the F3 intersects with the y-axis. Because it intersects with the y-axis, again, it does not generate any moment. So it intersects with the y-axis, it does not generate any moment. It doesn't make any rotation because it intersects with the axis, it does not make any rotation, so there is no moment. So m about y is then, it's going to be positive 150 Newton meter. So again, for the y, if we have the force is parallel to the axis, it does not make any rotation, so it does not make any moment. If the force intersects with the axis, again, it does not any rotation, it does not make any moment. And for moment about the z, we start for the F1. So F1 intersect with the axis, so it's going to be because it intersects with the axis, it does not generate any moment, it just intersects with the axis, with the z-axis. F1 intersects z-axis, doesn't generate any. F2, if you look at the F2 rotates around, it creates a rotation around the z, and the distance is rotated just that, so it's going to be 50, and the distance of it rotate, it causes the rotation, the distance, the normal distance between F2 and z is 2. Is it positive or negative? So it created rotation in this direction like that, so it rotated direction like that. And if I put down a finger, my thumb is going to be in the negative z, so the rotation sign, so the magnitude is going to be negative. And then for the F3, the magnitude is 200, and it is parallel to the z, so it does not generate any moment. Again, it's going to be 0. So the mz would be negative 100 Newton meter. The same here. If you have a force parallel to the axis or intersect with the axis, it does not generate any moment, and the moment is 0. They're not, the parallel forces or intersect forces with the axis does not generate any rotation, so there's no rotation, there's no moment, and the moment would be 0 for them. So that's how we calculate the moment about x, y, and z axis if we have the normal distance to those axes. Okay, let's look at another example how to calculate the moment of force about a given axis. Here we have a force 100 Newton, which is parallel to the y-axis, and want to see how much moment it creates about the MO. In other words, want to calculate the moment about the OA axis. If we remember, when we wanted to calculate the moment of force, so we had that we have the position vector about the axis. So it's a position vector about the axis, dot product R cross F. So that's how we calculate the M about OA. So M about OA is the unit vector about the axis, dot product R cross F. And if you come here and look at that, now I know the unit vector is about the OA. The R, it can be any vector, start from the OA, start from the axis, and end on the line of action of F. So here I'm going to choose OB for my position vector, but also I can get A and B. I can get the AB or RAB, because A is on the axis and B is on the line of action of F. So also the AB was is correct, you can get that. Here I get the OB, you can get the AB as well, or any other position vector that start from the OA and end on the line of action of the force. So to calculate that, we're going to first start to find the UOA, and we know that the unit vector is the position vector divided by its magnitude. So we have to find that UOA first. We have to find the position vector for OA and then use it for our calculation. So I come here and I start to write it here. So the ROA, which we needed here to calculate it, is going to be X A minus XO I plus YA minus YO J plus ZA minus ZO K. So we need the coordinate of A, O, and A, and later on we will need the coordinate of B. So I'm gonna write the coordinate of these points. So for the point O, we know that it's gonna be 0, 0, 0. For the point A, it has a x of 2, it has a y of 4, and has a z of 0. For B, again, it has a x of 2, it has a y of 4, and has a z of 3. So if I come here and substitute this value, the ROA is going to be 2 minus 0 I plus 4 minus 0 J plus 0 minus 0 K. We don't need to write 0 K, but because we use it later in calculation, so I keep it there. Now the UOA is going to be the ROA divided by its magnitude. So it's going to be ROA divided by its magnitude, which is going to be 2I plus 4J plus 0K divided by 2 squared plus 4 squared plus 0 squared, and then it's going to the UOA would be 0.447 I plus 0.894 J plus 0 K. So that is the unit vector along the OA axis. The next thing we need is the ROB. So we need that position vector. So the ROB is XP minus XOI plus YB minus YOJ plus ZB minus ZOK. And if I substitute, then the ROB will be XB minus XO is going to be 2I plus YB minus YO is going to be 4J, and it's going to be ZB minus ZO is going to be 3K. So this is also the ROB. And the last thing we need is the F itself. And if we look at the F itself is only in the direction of the Y. So because it's in direction of the Y, it only has the J component. It doesn't have an I component, it doesn't have a K component, and it's the positive direction of the I. So it's going to be 100 J. It doesn't have any I or J, I or K component. So now we have all vector we wanted. So I'm going to write them here and clean the other side. So I know the unit vector that I have is 0.447 I plus 0.894 J plus 0 K, and the ROB is 2i plus 4j plus 3k, and f is 100j. So these are all the vector I need to use in my calculation. So I come back here and write it here. So to calculate the moment about OA, again I'm going to write it right here. It's going to be U OA dot product R OB cross F, and we know that this is going to be as a determinant. If we can write it as the UOA in the X, UOA in the Y, and UOA in the Z component, and then ROB in the X, ROB in the Y, ROB in the Z, and then FX, FY, and FZ. So if I substitute the value here for unit vector, is going to be 0.447, 0.894, and 0 for the OB is going to be 2, 4, and 3, and for F is going to be 0, 100, and 0. And if we do the calculation, if we calculate this determinant, what we will get is write it a little bit. So we get minus 134.1 Newton meter. So it's the magnitude of moment about the OA axis, and if we want the vector MOA, we know that it's going to be the unit vector OA. It's going to be the magnitude times the unit vector. So it's going to be the magnitude of moment about OA times UOA. So that's what we are going to have. And then the magnitude, we know that the magnitude is minus 134.1, and the UA is this. So it's going to be 0.447i plus 0.894j plus 0k. So that's the, and if and we can expand it, so times each term by the magnitude, so it's gonna be the vector. So that's how we get the magnitude of the moment about the OA, and this is how we get the vector of moment about OA. So very quickly, what we want to calculate, we need to find the unit vector along the axis. When we want to find the moment about the axis, we need to find the unit vector along the axis. Find the position vector that goes from any point on the axis to any point on the line of action of the force and the force. So we find these three vectors, and after we find these three vectors, we put it in this determinant and we calculate the magnitude, and then we can calculate the here the vector of the moment about that axis.